Alright, so today in this lecture what we're going to talk about is the basic kind of equations for turbulent transport. So, as we talked about in last class, turbulence has many different properties. One of them is random-like motion. So if we have a general signal, let's say we have the u velocity and we have time on this axis, we have some signal that is going to appear to be semi-random through time. It's going to go through it. And we talked about that. One of the things, while these signals appear to be random, in general, if we look at the statistics of the signal, they appear to be fairly well behaved. In fact, some things like the mean and the standard deviation, as we saw in our example from the sonic anemometer data, look to be fairly well behaved. So one of the general ideas, it's the oldest and the most well-recognized ways to look at the equations is to think, instead of thinking of the instantaneous equations that the Navier-Stokes equations solve, we instead look at what are basically the average equations. So we think of taking our flow and we're going to decompose it into two components. We'll say that any u velocity, instantaneous u velocity, can be decomposed into an average velocity plus a deviation from that average. Which basically, if we look at this graphically, what we mean is that we can take the flow, we can take our average, u bar, in this case an average in time, and this average itself is usually looked at to be an ensemble average. So this is where u bar is an ensemble average. And what do we mean by an ensemble average? Well, an ensemble average basically means an average of independent realizations. So this could be in time, which means that you need to be over a long enough time period, or you need to be, your set of variables that you include in your average need to be independent of each other enough. Or it could be that the ensemble is a set of different types of simulations. So you could have several different realizations that change in time that you average over all of those different realizations. So say multiple time series. That would also create an ensemble. Think of just the word ensemble and how you've seen it in different contexts. But it could also be a spatial average or a time average. So we'll use right now these angle brackets to denote an average. Where now the u prime, or the fluctuating component, is basically our deviations from this. So this would be u prime. And u prime can be both positive, right? These would all be u prime values here, or it can be negative. We can have fluctuations that go below the average. So this would be u prime. This is also u prime. So it's all these little deviations that we want to go up through. So that's what we're going to basically say, is that any flow field can be decomposed into these two components at any instant in time. So if we're at this point, it's our average. This value here is equal to this u prime plus this u average as we go through it. And this idea was first introduced by Reynolds. So this is usually called Reynolds averaging. And a Reynolds operator is basically a symmetric operator that commutes with that, or basically we can say it's that follows that adheres to the following rules. Basically, that our average will, and this is in the end the most common one of these that is used to do this is most common for Reynolds averaging, the most common Reynolds operator is our typical average, right, that we already know of. So this would be where you would, if you want discretely, you would say that u bar is just equal to 1 over n times the sum I equals 1 to n of basically all of our ui's in our set. Right, so it's just going to be the average through this. Or you can write this as an integral equation where you would average over your spatial or whatever your set is made of, or time, or your ensembles, if you did it as an integral. But this would be kind of our typical discrete one. So the rules that are rules for a Reynolds operator are as follows. So the first rule, and this comes straight from our definition of the average, is that the average of any coefficient or any constant value times our variable, so a times u, is going to be equal to just a times the average of u. So basically it commutes, we can basically move any constant, and this is where a is a constant. So our random variable, right, and u is our random variable. For us, that means the velocity field, but in general, it just means a random variable. For any constant multiplied by a random variable, we can move the constant outside of the Reynolds operator. And again, if you think of just simply our sum, if we have a constant here, just like this 1 over n is a constant, we can move it in or out without any loss or any change in the actual what's going on. We should also, if we have two random variables, say u plus v, say two velocity components, we can separate these out and write these as u plus v in a very, very straightforward manner, where now we also have v as a random variable. So it just follows these kind of rules of averaging. Another important one for us is we know in the end we want to apply this to the Navier-Stokes equations, is that for Reynolds operator we also commute with differentiation. So if we have some term like the partial derivative of u of our random variable with respect to x, the differential operator, which is a linear operator, again, if we think of our sum, linear operator can move in and out of our sum as well, or out of an integral if we have that. So that means that we can write this simply as partial derivative with respect to x of u without any loss in that case either. Simple enough to do. The fourth rule, that will also be an important one for us to use, is that if we take the average, the ensemble average of all of our deviations, so if we're looking at our deviations here from our mean, if we take the average of those deviations, if our operator is properly applied, we should get 0. Right? So basically we add up all the fluctuations off of here, they should give us 0 on average, if this average u ensemble average is actually representative. And similarly, we can say the same thing, that if we average twice, so we take a variable that's already averaged, our random variable, we average it, then we average it again, we simply get the average. So the average of the average is the average. That's our kind of other rule. So what we want to do is let's apply these rules to decompose the conservation equations into mean and fluctuating components. So we basically want to take conservation of mass and conservation of momentum and put this into it. So let's look at conservation of mass first. So we'll just do this for an incompressible flow. You can also do it for compressible flow without much loss in generality. There are some different details for compressible flow that are usually used to make things simpler to analyze in the end, but the general idea stays the same. So our equation that we start out with, we just have for incompressible flow, dui dxi is equal to 0. So what do we want to do? We want to use the fact that we want to use our decomposition. So we're going to say that ui is basically equal to the average, the ensemble average of ui, plus a deviation. So our instantaneous ui at any point in space is equal to the average at that point plus the deviation from the average at that point. So inserting this in, what we get, straightforward, we get partial derivative of the average ui plus ui prime dxi equals 0. Now, what we're going to do is we're going to take the average of this average. Remember, we can average twice in that. So we'll now take the average of this. Because remember, this decomposition, when we've inserted this into this equation, we haven't changed anything. What we want is an equation for the average. We want the average equation. So that's what we're going to do. So we're going to take the average of this equation. We'll go on to the next page. And when we do that, now what we have is by taking the average, we'll now have what will basically be something that will look like this. We'll have the average of the partial derivative of the average ui plus ui prime with respect to x is equal to 0. And now we can use some of our rules. So first, we're going to use Rule 3, which said that we can basically move our derivative in and out of this average. So use Rule 3. With Rule 3, that says that we can write this as dx of, and down inside here we'll have the average of ui plus ui prime equals 0. We can now go and use Rule 2, which says that we can separate out two things that are added together, right? If we have the average of two random variables together, added together inside, we can separate those out. So if we do that, we can now write this as, so now we'll use Rule 2, and with Rule 2, we can now write this as dx of the average of ui plus ddx of the average of ui prime. It's going to be equal to 0. So now, if we use Rule 4, right, which Rule 4 says that the average of the deviations is 0, so use Rule 4, that says that this term is 0, because the average of the fluctuation is 0, and we know that the average of the average is the average, so with Rule 4, we're left with that partial derivative of the average ui dxi is equal to 0. Or if we want to sum it up, basically, our Reynolds average conservation of mass says that the conservation of mass holds for the average just as it holds for the instantaneous. So, conservation of mass holds for the average the same as for the instantaneous velocity. Alright, and that's a nice way we can demonstrate the different rules. So, now as we move on, what we want to go to is we want to look at conservation of momentum. So now we have conservation of mass, now we want to look at conservation of momentum. So we have one of our equations, so conservation of momentum, or our Navier-Stokes equations, and for incompressible flow, what are we talking about? We'll do again, this is just incompressible flow. We have that dui dt, this is our starting equation, plus d, and we'll just write it this way, ui uj dxj is equal to minus dp dxi plus 1 over re times second derivative of ui with respect to xj. Plus whatever forcing or body terms that we might have when we go through that. Where here we've moved the two terms together, so this term, if you know, usually we write this out as uj dui dxj, but we can use our product rule to show that this, right, if we do the opposite, let's take this one and expand it. If we expand it, this is just going to be equal to derivative of the first one, so dui dxj times that, so there, plus, then we'll have derivative of the second one times the first one, so we'll have ui duj dxj. But by conservation of mass, this term is equal to 0. So we can move, what this basically says is that this and this are equivalent, and we can move this ui in and out for an incompressible flow for this type of thing. So we have it there. So now what do we want to do? We want the same thing. We're going to decompose this using basically that u is going to be equal, ui is equal to the ensemble of ui plus fluctuation from the ensemble. So let's just go ahead and stick that in. Do that for each term. So our first term becomes d partial derivative with respect to t of, and here we'll have ensemble of ui plus ui prime, plus we'll now have this term here, our nonlinear terms. This will be d dxj times, and now here we'll have two different terms. We'll have, let's do a square bracket around that, we'll have ui, ensemble of ui plus ui prime times ensemble of uj plus uj prime is that term. Our pressure term, we can break that out into a fluctuation and a mean as well. So we can say that this is going to be equal to minus, we're decomposing our pressure in the same way. We'll have here dxi of, in this case, the ensemble average pressure plus the deviation from that. Go through that. We'll also have our viscous term. So we'll have a plus, and then this term will end up being 1 over RE, will remain a constant, times second derivative with respect to xj of the ensemble of ui plus the fluctuation from ui plus, and we'll just say our forcing term, we're just going to leave that as fi for now. We'll say that that stays kind of as is. So now we need to go through each of these terms. Again, what's the next step that we're going to do is we're now going to average the entire equation. So now average the entire equation. Alright, so we want to take an ensemble of all these, and we know by our rule number 2 that we can actually take each of these terms and we can look at them separately, look at the average of each of these terms, right? That's what rule number 2 says us. So by rule 2, we can look at each term individually. So we'll have here, we have term 1, here we have term 2, we'll call this term here term 3, call this term 4, and this will be term 5. So let's look at term 1 first. And hopefully this all looks pretty straightforward by now, as you can see the pattern for how this starts to go. So term 1 basically just says that we have the average of dt, partial derivative with respect to t, of the ensemble average of ui plus ui prime, all averaged. We can now use rule number 3 to move our derivative outside of this ensemble. So we use 3. That lets us write this as partial derivative with respect to t of, and we can also we'll use rule 2 as well, 2 plus 3. So that lets us separate it into two things, and so we'll have the ensemble average of ui plus partial derivative with respect to t of the average of ui prime. So we'll end up with here. And now by rule 4, we know that this is 0 and that this is just ui bar. And this is by 4. So that in the end, for term 1, it will just be that partial derivative with respect to t of ui ensemble averaged will be what term 1 reduces down to.